Alright, so this video is going to be about something called Hooke's Law, and Hooke's Law has to do with springs, so this is pretty much going to be the universal symbol for springs. Okay, just a kind of a coil, it looks like a slinky kind of thing. Just kind of a historical outlook. Hooke lived at the same time as Newton, and Hooke and Newton kind of had arguments about a few things. Hooke's Law was the only thing that he's pretty much known for. There's a few other things, but in terms of high school physics, this is the only time that we're ever really going to talk about Hooke. But it has to do with the force about springs, the force on a spring, force by a spring, that kind of thing. So some of your observations that you saw in class were things like a spring always returns to its original length. Okay, so if we had something along the lines of a slinky or a spring that did something like this is the original length, and we apply a force to it, there's an F, then it might stretch, and I'm going to put the stretching in kind of a dotted line here. Okay, it might stretch all the way out to here. So we would say that how much it stretched away from its original length would be its extension, or its distance, or position, or whatever we're using X for. Here it says that it's used for extension. Extension. Did I spell it right? I think I did. Okay, so it's extension. But if we were to then nix that force, take that force away, then the spring would immediately go back to its original position. Same kind of thing would happen if we compressed it. If we were to add a force that went this way, then it could be compressed all the way up to, and I'm going to do this in blue, maybe it compresses it all the way up to here. Okay, it compresses it as far as it goes, maybe. Okay, that means its new extension would be out to this way. Okay, but notice how this one went to the left while the other one went to the right. So that means we can actually have two directions here, like what we've been doing in class. Directionality is just given by a negative or a positive, so that means we might just say that that was negative. We say maybe compression is negative. It doesn't have to be that way. It's just that usually that's the easiest way to do it, is compression is negative. Some ways that it might not be as easy is, what if we're talking about a vertical spring? So maybe something's hanging down from the ceiling and we put a mass on it. So what kind of forces do we have on this object if we do a free body diagram? Well, we know we would have gravity. Let me get the right color here. Okay, we know we would have gravity, so there's the force of gravity. And we know that that would have to be balanced out by something, and this is what we're going to call the force from the spring, Fs, so the spring force. And in this particular case, it would have to be completely balanced out. Well, this force, though, this gravitational force, has caused the spring to stretch. So maybe it used to be, the end of the string used to be right here, we'll call that maybe an initial position, and it has stretched all the way down to this. So that's an extension. But that extension is going down. So it would be, maybe we would call this a positive because it's extending the spring. But take a look at the directionality of the force. The force is going up. And the same kind of thing would happen if we were to compress the spring. Maybe we did it over here. We compressed the spring. This is the force that we had to add to it in order to compress it. But the spring itself would be pushing back on it. So what we're talking about here is that the force from the spring, it seems to be always be in the opposite direction of what is happening with the spring. If you're compressing it, then the force is trying to push it out. If you're extending it, then the force is trying to bring it back. So the force is trying to keep that original length. It's trying to get back to that original length. Okay? That original length, we usually have a name for it. It's called its equilibrium. Okay, it's its equilibrium position. So when we say a spring, wants to go back to equilibrium, that means that the force is trying to get it back to its original length. So when we talk about forces on a spring versus forces by a spring, then we're really talking about what's going on in terms of free body diagram. Just like what we had with this guy, this is the force by the spring. Okay, that's the force by the spring, but it shows up on the free body diagram for our box. Okay, a force on a spring would show up on a free body diagram for the spring. Okay, you can kind of see the difference there. We don't usually care about the forces on a spring. We really care about what the spring force is by the spring. But according to Newton's third law, we know that the force on the spring and by the spring should actually be equal. They'd be on two different objects. So that means whether this is on or by, it doesn't really matter. It's the same force. And here, we know that force would have to actually be equal to the gravitational force. This one and this one would have to be equal to each other. So what Hooke's law actually talks about, again we come back to Hooke, his name was Robert Hooke. Hooke's law actually talks about the relationship between force and the extension of the spring. What he comes up with is that the force is equal to some constant that he called K, and K is known as the spring constant. Okay, but like what we just figured out was that the force is always in the opposite direction. The force here is in the opposite direction of that position. We have to throw a negative into this equation just to make sure that it works out, directionally speaking. So the force is in the negative direction as opposed to a positive x, or the force would be a positive if we had a negative x. And it all works out in this equation right here. So this is a very nice equation. It pretty much means that they are directly related. Well, actually, it does mean that they are directly related. So if you double the force, that's going to lead to doubling the extension. Okay, if you halve the force, then that halves the extension and things like that. So let's go back to this K real quick. This K is called the spring constant. It's basically how stiff the spring is. So if the spring is very stiff, then a force might not extend it very much. If it's very loose, like a slinky, then the same force might extend it a lot. So let's say we care about what that spring constant is. So the K, if we solved it from this equation here, right, F is equal to Kx, negative Kx, then what we would have is force over extension, F over x. Technically, yes, it would be negative F over x or F over negative x, but all that would do is just make sure the directionality works out just right. So let's talk about the units for K. So the units for force are newtons. The unit for extension or position is meters. So K is talking about newtons per meter. So if the spring constant for a given spring was 500 newtons per meter, that means it would require 500 newtons in order to stretch it or compress it 1 meter. Okay, but what if we don't compress it 1 meter or stretch it 1 meter? What if we only compress it half a meter? Well, then that means it would take 250 newtons. Okay, that goes back to that whole direct relationship between force and extension. So what we're going to be doing in class is taking a closer look at this relationship and see if we can't derive it ourselves in a very short lab that we're going to do when we come back. Okay.